Hi, in today's video we're going to take a look at another handheld oscilloscope from DreamSourceLab. For those who are following my channel, you might recall that I reviewed a DS4T252 from them a little over a year ago, and I was actually quite impressed by its performance. The DS Touch series of the oscilloscopes are touchscreen operated. The scope has a 150 MHz bandwidth, a sampling rate of 1 gigasamples per second, and it has 16 megapoints of waveform storage depth. It also supports protocol decoding, FFT spectral analysis, and even comes with a built-in function generator. The only downside of the DS4T252 in my opinion is the price. For a lot of hobbyists, the $200 plus price point is just a little bit too high, and a lot of people probably would not need the 150 MHz bandwidth anyway. So DreamSourceLab recently launched a new entry-level scope, the DS4T252, which is what I have here on Workbench. It has a respectable 50 MHz bandwidth with a sampling rate of 200 megasamples per second. And by the way, the product link is in the video description below. Now, you might think this is just a scaled-down version of the DS4T252, but there's one feature on this DS4T252 that is actually better than the higher bandwidth version. And that feature is a maximum vertical sensitivity. On the DS4T252, it is spec'd down to 1 mV per division, compared to the 10 mV per division on the DS4T252. This is definitely a welcoming feature, as most of the portable scopes only go down to 10 mV per division. Having a 1 mV per division sensitivity would allow you to work on lower signal level circuitry, such as small signal amplifiers. Besides the bandwidth and higher sensitivity, all other features are identical to the DS4T252. The 1 mV per division sensitivity is traditionally only supported on mid to high-end desktop oscilloscopes. This is actually the first time I'm seeing this specification on a portable scope like this one. So I'm definitely excited about that. Price-wise, the DS4T252 is priced just under $100, which makes it even more attractive. Now let me put the DS4T252 and the DS4T252 side by side, and you can see that they are virtually identical. On the left side is the DS4T252 and the right side is the DS4T252. You can see that they are essentially the same. They have the same dimension, they have the same layout, and everything about them looks exactly the same, except if you look carefully on the back here. Of course, now I just get them mixed up. On the DS4T252, you can see we have this 150 MHz bandwidth and 1 gigasamples per second printed, whereas on the DS4T252, the label is 50 MHz and 200 megasamples per second, with a 2 megpoints storage depth, whereas on the DS4T252, it's 16 megpoints storage depth. So that's the only difference. As you can see here, the carrying cases are also identical. So are the accessories supplied. So let's open up and see what we got. The carrying case is actually much larger than the scope itself. The scope is fitted in the middle here. You can see we have this supplied instruction manual, which is a basic getting started guide. And here we have by the look of it, a USB cable and an MCX to BNC connector. That's for the signal generator output. And then we have the probes. Now, the supplied probes are actually different than those supplied with the DS4T252. That's because the bandwidth, which is to be expected. These are just your run-of-the-mill P6060, whereas the ones supplied with the DS4T252 are the P220 200 MHz version. These P6060 probes are only rated for 60 MHz, but given that we only have a 50 MHz oscilloscope, these are sufficient for the job. The scope is as small as it gets, yet it has a 4.3-inch display. Because it is a touchscreen, DreamSourceLab did away with most of the physical controls, except for a couple buttons you can see up here. One is for stop and resume, the other one is for auto acquisition. Now, to squeeze everything into this tiny package, DreamSourceLab had to make some careful design choices. For example, we have two BNCs here on the side for the oscilloscope input channels. But for the signal generator output, they opted for an MCX connector instead, as here we simply just don't have enough space for another BNC connector. I actually think this is a good compromise, as the primary function of the device is oscilloscope after all. And just to give you an idea of how small the DreamSourceLab's oscilloscope really is, here I have a Finersi 2C53P that I reviewed a few months ago. It actually also has a 4.3-inch touchscreen, but overall it's much bigger in all dimensions. And let me just show you here. Let's put it side by side. You can see it is longer and also it is much thicker than the DS4T252. And of course, you can see here, it is quite a bit wider as well. Of course, the 2C53P has a built-in multimeter. You can see we have the sockets here, and of course this one does not. But I just wanted you to appreciate the small size of the DreamSourceLab scope. It also has a stand on the back, which gives you two positions. You can stand it up. For example, this is position number 1, and also you can lean it further back. Now the lighting in this lab is not ideal, so I probably have to shoot the video with the oscilloscope on its back without the stand, as this probably will give you the best viewing angle with least amount of glare. And I just turned off one of the overhead lights, so hopefully it shows on camera better. Let me remove the protective film on the screen first. Alright, let's power it on. The power button, as you can see, is on the side here, so let's press it. And you can see it powered on almost instantaneously, just like the 4T1012. In fact, the user interface is identical on this DS4T252 compared to the DS4T1012, so I won't spend too much time on the user interface itself. If you wanted to learn more, please check out my DS4T1012 review video, which I will provide a link in the card up there. By default, the trace is stopped when initially powered on, but you can change the power on behavior to remember your last session parameters in the system manual. To enable the trace, you have a couple of options. You can either use the on-screen menu to enable it, or you can use the run and stop button on top of the unit to start and stop the trace. Now the trace looks thicker than usual. That's because we're currently at 2 mV per division. So let's actually change that. And we can change it to, we can use the scroll wheel here, you can see that. Let's change it to 10 mV per division. And by the way, you can see the default channel color is pink. But again, you can change it to a color that you prefer. I personally prefer the standard color, so let's change it to yellow. So we come to color, and you can see we can change it to yellow. And it's easy as that. Now I have hooked up a signal generator to channel 1, and let's actually put in a 1 kHz 1 volt peak-to-peak square wave and acquire the signal. So let me enable the signal generator output. And by the way, you can see here we have an overrange indicator here. That's actually something most entry-level scopes don't have. And this is actually a feature I really like in this DS Touch series. This is useful when measuring an unfamiliar waveform, as when you see this indicator, it means that you need to reduce the vertical amplification as the signal is cut off. Without the indicator, you could easily misinterpret the signal, especially if you don't know what you are expecting. Anyway, let's do an auto acquisition on the signal. To do that, you also have a couple ways. You can either use the auto set button, that's a touch screen here, or you can use the physical button located on the right hand side on the top of the unit. Let's do that. So you can see we acquired the signal with no problem. There are also multiple ways to adjust the amplitude and time base. Just for a quick demonstration, you can press the upper half of the screen here to increase the time base, or press the lower half of the screen here to decrease the time base. Alternatively, you can use the single-handed operation mode to achieve the same thing. To activate the single-handed operation mode, you can press and hold anywhere in the white space to the far left. And then we can change, let's say we want to change the horizontal, then you can use the scroll wheel to achieve that. Very convenient. To change the vertical scale, of course, you can go to the menu here and scroll up and down to change the scale. Or you could use the one-hand operation, like what we showed before, to change the amplitude here by scrolling up and down. And while we're here, let's do a couple of measurements. So let's enable the measurement. Let's say we want to see the frequency. Also, we wanted to see the amplitude. And you can see here, we are at 1 kHz and 1 volt peak to peak. I have to say that I'm pretty impressed with the UI design, as it's clean, responsive, and very intuitive to use. Now, one of the most impressive features of this scope is that it has a 1 mV per division vertical resolution. So let's actually take a look at that. Now I'm outputting a 2 mV peak to peak 1 kHz square wave from my UTG-1042X signal generator. Now 2 mV peak to peak is the lowest I can output from this signal generator. So let's actually adjust the vertical scale here. Let's come here. Let's do 1 mV per division. And you can see we captured that signal with no problem. Of course, the noise you see here is somewhat to be expected, as now we're down to the 1 millivolt per division range. And by the way, let's actually turn off the signal generator output, and let's see what we got as a baseline. You can see that the baseline is roughly at about 500 microvolts, I would say, give or take. So the noise you see is actually mainly from the oscilloscope acquisition. So let's enable the output again. And let's try another waveform. Let's do sinusoidal. And you can see the sinusoidal is actually pretty clean here. And let's change it back to square wave. I should have pointed out earlier that the ADC used in DS Touch series is 8-bit only. But you can see that even at 1 millivolts per division, the noise level is quite decent. It would be nice if DreamSourceLab can provide a 12 bits front end in a future model, but that would probably be a lot more expensive. Alright, next, let's check out the 50 MHz bandwidth claim. If you remember, the DS4T25252 actually met its 150 MHz bandwidth claim with no problem, so I don't think we're going to see any problems with this DS4T252. But I'm actually interested to see the bandwidth situation when both channels are enabled, as the sampling rate would drop to 100 megasamples per second when you have two channels on. And with an input frequency of 50 MHz, you are only going to get 2 samples per waveform. So that is the bare minimum needed to reconstruct a pure sinusoidal. So let's actually give it a try. To ensure we have correct impedance matching, I'm going to add in this 50 ohm through adapter. And currently, I have already adjusted the signal generator output to 1 MHz, 1 volt peak to peak. For this exercise, I actually swapped in my DG2070, as that signal generator is capable of outputting 70 MHz versus the 40 MHz tops with the Unity UTG1042X. And let me enable the output. The output frequency right now is set at 1 MHz with an amplitude of 1 volt peak to peak. So let's give it a go. And of course, we need to reacquire the signal. And you can see here is signal. Let me change the amplitude scale a little bit, and so it's easier for us to see. Okay, so I think I can also enable the cursor here. Let's do that. And let me move the cursor up. So now you can see here that's a 1 volt peak to peak, and also the amplitude is being measured here as well. Alright, let's increase the output frequency here. So now we're at 10 MHz. You can see no problem. And let's decrease the time base as well. So this is 10 MHz. Let's do 20, 30, 40, 50. And now we're at the bandwidth limit, and you can see we're still getting about 750 millivolts. Let's just verify that. And you can see from the cursor measurement, it's actually 800 millivolts. There is some discrepancy between the measured amplitude versus what is reported here. Let's just fine tune it. Yeah, 786, give or take. So for single channel operation, definitely it meets its specified bandwidth. Let's actually push it a little bit. Let's change it to 60. And you can see we are still able to measure the waveform. Of course, it becomes a little bit wobbly here. 70. Let's actually see what's the amplitude here. Yeah, so this is already below the 3 dB bandwidth. So definitely the bandwidth is somewhere between 50 and 70. So let's do 60. Let's see if we can measure the amplitude here. So I would say it's probably around 55. Let's just go to 55. Yeah, as you can see, with a input frequency of 55 MHz, we're measuring about 720 millivolts, so that's right around the 3 dB bandwidth. Now let me change it back to 50 MHz, and I'm going to enable the second channel to see what we got on the screen here. So let me enable the other channel, and as I somewhat expected, we're not able to capture the waveform. The reason is because we only have a 200 megasamples per second sampling rate. And when you enable the second channel, each channel is only going to get sampled at 100 megasamples per second. So definitely that's not really sufficient to capture the waveform cleanly, as you can see here. So let me reduce the input frequency here to see, yeah, so for example, right now we're at 47 megahertz, and you can see we capture that with no problem, 48, and it's getting there. So when both channels are enabled, you are able to get pretty close to the 50 megahertz bandwidth, but not quite. So right now, for example, we're at 47 megahertz, and the displayed waveform is pretty good. So as you can see on this scope, when both channels are enabled, the maximum bandwidth is just shy of 50 megahertz. And that is limited by the maximum sampling rate of 200 megasamples per second. And here I'm showing an amplitude modulated signal. It is a 1 MHz carrier with a 1 kHz modulation, and the modulation depth is set at 100%. And you can see we're able to get a very stable capture with some adjustment to the trigger position and also the trigger hold off. And what I'm showing you here is a frequency modulated signal. The carrier frequency is still set at 1 MHz. And the modulation frequency is set at 100 Hz with a frequency deviation of 100 kHz. You can see just how fast the update rate is. And now let's do a single shot. And we just captured the power on characteristics of a power supply. The memory depth of the scope is 2 megasamples, which is plenty for you to do more detailed analysis. The DS4T252 also supports FFT, and let me do a quick demonstration here. So to enable FFT, we can come here and enable the FFT. And let's take a look here. Once enabled, of course, we can come here and fine-tune the options here. So right now, I can set the center frequency. Let's do 5 kHz so that we can shift the display to the left a little bit. And the range is 12 kHz. Let's do it a little bit higher. 25, 29 kHz. Okay, looks good. So let's come back here, and you can see we have different peaks corresponding to each of the harmonics of this square wave. And let's change the frequency again. Let's say the range, let's do 10 kHz. And now you can see the frequency components in higher resolution. And now let's take a look at the Lissajous figure. Let's enable the functionality here. XY mode. Now let me change the phase relationship between these two 1 kHz signal. So let's do 10 degrees, 20, 30, 40. You can see that. And now we're at 90 degrees, which is a perfect circle. And now let's vary the frequency of one of the signals. Now I'm going to do 100 Hz at a time. And you can see the display is actually very sharp. Very nice. You can also swap the X and Y channel. Just like the DS4T1012, the DS4T252 also supports protocol decoding. It can decode UART, SPI, and I2C signal. Now what I'm showing you here is the decoding of the UART data coming out from an Arduino board. You can see it says hello world. Let me just pause the frame here. And you can see the message that's being decoded here. Let me just let it run again. And let's pause the display here. And you can see the hello world being decoded here. And let me just show you the setup here. So you go to more, and then you get I/O, and here is your decoding manual. You can see we are currently decoding UART with a baud rate of 9600. And here is an example of the captured I2C data. As you can see, we are able to capture the clock and also the data frame. And if you remember, one of the issues I found during my testing with the DS4T1012 was that the captured avalanche pulse waveform was incorrect. I actually contacted DreamSourceLab about that issue, and they specifically mentioned to me this time that the issue had been addressed. So let's test it out here. And now I just hooked it up with my Avalanche pulse generator, so let's power it on. By the way, the Avalanche pulse generator generates a very short pulse that is useful for measuring the rise time of the scope. So let's actually do some auto acquisition here. Of course, most of the time you can't really auto acquire it. Let's drag it down a little bit. And let's expand the pulse. And let me move the trigger a little bit. And as you can see, the measured pulse is actually very clean, and this is definitely the right shape of an Avalanche pulse. Let's actually do some measurement here. Let me pause this and do the vertical cursor here, just to get an idea. So this is roughly where it starts. If you look at the screen here, you will see we measured a rise time of 5 nanoseconds right here, and that translates into a bandwidth of 70 MHz. This is actually pretty consistent with what we saw earlier. Now, the main constraint of this oscilloscope is not the analog portion, but rather the digital portion. As for dual-channel operation, the sampling rate is only at 100 megasamples per second for each channel, so that only supports a maximum 50 MHz of bandwidth. And just to remind you what the issue we saw with the DS4T252, I had swapped in that oscilloscope. We're currently observing the same Avalanche pulse train. So let me zoom it in. And you can see here is the acquired signal, which definitely does not look correct. And just for comparison, here is the Avalanche pulse captured by the DS4T252. If I have to guess, they probably fixed the filter response in the original DS4T1012, as this is just implemented in the DSP, so they can easily fix it in the firmware. So let's actually take a look at the version information. And you can see right now on this DS4T252, we have version 1.0. Let's see what is the other one. Yeah, you can see on the DS4T1012, we have 0.99T. So definitely the firmware has been updated on the DS4T252. And now I just want to briefly demonstrate the built-in function generator. Because I have both of these scopes, I'm using the DS4T1012 that is up here to monitor the output from the DS4T252 that is at the bottom. So let's go to the menu here, More, and the first one you can see that's our signal generator. Let's just enable the output here. So you can see we're actually currently outputting a sinusoidal that is at 1 kHz, and we can of course change it to square wave, change it to ramp, and so on and so forth. And you can see that these are the stock signals. Fairly basic, but you do have a variety to select from. So let's go back to, let's say, square wave. And we can also change the output frequency. You can see that we can use the scroll wheel to change the frequency here. The maximum output is actually only at 100 kHz. So let's do this. Let's see if we can get that. Yep. So you can see that's our 100 kHz square wave. And that is not that high by any stretch of imagination, but it should be sufficient for your basic testing. Again, let's cycle it through. Let me move this down a bit. Again, let's cycle it through. Sinusoidal, triangular wave, and ramp signal. And the output amplitude can be adjusted continuously between 0 and 3 volts. And let me show you that. You can see that we can adjust it downwards and adjust it upwards. And of course, we can also adjust the minimum. And of course, we can also move them around. So you can see that's actually quite useful. There are some functionalities I haven't touched upon on this DS4T252, and that's because they're identical to that of the DS4T1012 I had reviewed before. So if you want to learn more, please check out my review video of the DS4T1012, and that one covers everything in depth. Also, I won't be doing a teardown in this video, as I think the internals will be very similar between this DS4T1012 and DS4T252. The only differences would be the FPGA and the DRAM used. I will leave a link to the DS4T252 teardown video here, so you can get an idea of what the unit looks like inside. For less than $100, the DS4T252 is a very attractive portable oscilloscope, in my opinion. Unlike some other oscilloscopes I have tested on the channel, there is no exaggeration in the specs, and the scope delivered everything it promised. Its UI design is certainly in a different league all by itself. Anyway, I hope you enjoyed the video. If you liked the video, please remember to give it a big thumbs up and don't forget to subscribe to this channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.